Hello, good afternoon. We are here to present you some words about decarbonizing beyond electricity and the role that nuclear could play. And we will focus mainly on the role that nuclear could play in the production of hydrogen. So my name is Bertrand Charmaison. I'm heading ITZ Research Institute in CEA, which is our research institute in energy economics. And I will present together with Pierre Gallois, which
Hello.
The head of our SMR program. So there are two parts in our presentation. Again, the first part will be focusing on the hydrogen market, and then we'll talk about technical solutions that we could imagine to decarbonize and to produce hydrogen. So at first, why is there a need for low-carbon hydrogen for decarbonation? So hydrogen can be used as a feedstock. So it can replace methane, it can replace coal in hard-to-abate industrial solutions. But hydrogen is also a fuel that can be used, for example, to produce high-temperature heat. And finally, hydrogen molecule can be combined with other molecules to produce e-fuels like e-methane, e-methanol, e-kerosene, whatever kind of long fuels, long chains with carbons that we can use to decarbonize some sectors and the mobility. What is extremely important to stress is that hydrogen must come from low-carbon production process. Hydrogen is already produced today from steam methane reforming, but this process emits roughly 10 kilograms of CO2 per kilogram of hydrogen produced. So in order to decarbonize, it's highly important to produce hydrogen with low-carbon processes like water electrolysis, provided the electricity itself is low-carbon. So in which sector can we use hydrogen? So first, this low-carbon hydrogen can substitute to sectors where hydrogen is already consumed, like refineries, like ammonia plant, in order to lower the carbon footprint of these industries. That's one possible area of consumption. Another area is industries today where hydrogen is not consumed, but where it's not possible to electrify the process. And we can think, for example, to steel industries where hydrogen can play a role by changing the production process and produce low-carbon steel. And finally, and very importantly, for the mobility sector. In the mobility sector, you have some, for example, aviation and maritime transportation that will be extremely hard to decarbonize using electricity or other solutions. Hydrogen, in combination with other molecules to form e-fuels, seems to be the best solution to decarbonize these sectors. So let's look at the ambition that Europe has for hydrogen production. As you can see, the ambitions are extremely large. By 2030, so in less than 10 years, the EU objective is to have 20 million tons of renewable hydrogen produced in the EU. So this 20 million tons is 10 million tons that would be imported from outside the EU, but 10 million tons that would be produced within the EU. And just look at the figures. What does it mean to have 10 million tons? If you want to produce 10 million tons of low-carbon hydrogen with low-carbon electricity, it requires about 500 terawatt-hours of electricity to produce this low-carbon hydrogen every year. That's enormous amount of electricity. And just let's compare it to other objectives that are in the Repower EU package. For example, when you look at the objectives for wind turbines, the EU objective is 490 gigawatt. That's the objective at the EU level. So we can discuss what will be this production of these wind turbines, but roughly it will be about 1,250 terawatt hours. The objective is also to develop 600 gigawatts of PV, of solar PV, which would produce roughly 650 terawatt hours. So when you sum up and you compare that with the quantity of electricity needed for production of hydrogen, you see that clearly nuclear will be needed to achieve hydrogen nuclear production targets, because this renewable will also play a role for the decarbonization of other parts of the sector. Now what we try to do is, that are the objective in the political objectives. What we have tried to do is to try to estimate what could be the actual market for hydrogen and the derived E-molecules within the coming decade. And so this is a study we have performed during last year in CEA, and these studies have been supported by over 70 interviews with industrial stakeholders in France, in other parts of Europe, that cover more than 250 sites. So that's the main possible users of this hydrogen and these derived molecules. And we have focused here only on industrial uses and the mobility, meaning that solution power to X2 power have not been part of this study. And basically, we arrived to these results, which is our evaluation of hydrogen demand in Europe. As you can see, we see that the low-carbon hydrogen demand will massively increase in the coming years. So we have two scenarios, a high scenario, a low scenario. But just to compare that with the objectives, it's significantly below the objective. And why? Because we have identified with this interview, these discussions, many hurdles that prevent today the industrials and the mobility sector to achieve the targets that are set. One of them is about the instability and the change in the legal framework. Another is the lack of financial support, especially for OPEX to produce hydrogen. And very important one, a perception that there will be insufficient supply over the coming decade of low carbon electricity, of hydrogen, of CO2, but really a fear, independently of price issues, that there won't be sufficient low carbon electricity in the coming decade. So again, combining with what we said on the objectives and what we see from this bottom-up evaluation and these discussions with many stakeholders, is that nuclear is clearly needed to meet the decarbonization targets. Just to set a scene, this is basically our view of how the hydrogen market could develop. I'm not focusing here, it's more focused here in France, not all over Europe. We believe that there will be different chains, production chains that would compete against one another. Steam reforming and CCS, imports, more from the Iberian Peninsula than from large imports by ship, renewables, and nuclear. And here we believe that there are two main models. One is using the current fleet through PPAs. And as you can see, EDF is starting to sell electricity over the long term with PPA contracts. So these PPA contracts would source development of hydrogen production in France. And we believe that afterwards, somewhere into the next decade, it will be direct coupling between nuclear production facilities and hydrogen production facilities. And this competition, so we believe that in France we will have different filières that will compete. Green hydrogen in a way from renewables, produced from nuclear, and also imports. And all this will create a hydrogen mix that will be low carbon, and where France has really a very good position compared to other countries in Europe. I think we are late, and I will go just extremely fast. This is a study that can be found on, in Revue de l'Énergie, but basically what we see looking at the alternatives of the various chains, and with many assumptions that are depicted here that I will not detail further. We believe that in order to be competitive, the hydrogen production from nuclear and from coupled systems that we mentioned must target a production cost of around 3.5 euro per kilos of hydrogen. And now Pierre will explain you how we can reach this target.
Yeah, thank you, Bertrand. So I'll take from here and more specifically focus on the coupling side and the technical solutions we develop at CEA to couple nuclear heat and power with the electrolysis. So first, to just give you a broad overview of our work plan to address these issues of using nuclear heat and power beyond electricity, we developed basically an approach which focuses on 4 streams. First one being to study the markets and the uses there would be for heat and electricity for various branches of the industry. And then from these case studies, we can target new opportunities for nuclear heat and power to develop in combination with specific process and to define associated hybridization configuration. And then when we found these first use cases, we developed the technical and economical evaluations for each type of combination. The first one we saw was that there was a use case for SMR dedicated to heat, to low temperature heat, and just focusing on supplying heat to the market. The second one is to develop the coupling, like Bertrand mentioned, between an SMR and a high temperature steam electrolysis system to maximize the energy efficiency of the whole coupling. And we still, in the fourth stream, go on focusing on further needs, such as producing synthetic aviation fuel, which will be a big driver for the market in the coming years. So going first rapidly through the first use case, we saw that there was potential for the industry and also for district heating to make use of a supply of heat around 150 degrees C, and that from that we could derive and simplify very much a PWR design to just focus on producing heat at 150 degrees C, which would in turn, as a consequence, reduce the need to pressurize the reactor and simplify very much the design. So we developed a basis for this kind of design, and we have been working on the use case both on the district heating and also, which is heavily fossilized, as you can see on this graph, and also on the industry. So that's the first use case which we covered through our research. The second one, on which I will cover more extensively, is the coupling of a PWR type SMR with a high temperature steam electrolysis. Now, this process works at between 600 and 800 degrees C. So you see that there seems to be a mismatch in the heat and temperature level. But in fact, most of the heat you need to supply to this process is to transform the liquid water into steam. And that happens at 100 degrees C. And moreover, this process is exothermal. So you can use the excedentary heat of this process to heat up the steam to the process temperature of 600 to 800 degrees C. And as a consequence, we found that technically and also economically, it was viable and suitable to couple a PWR type SMR, for example, such as a new watt concept, with high temperature steam electrolysis to provide heat and electricity, and you can then derive even excess heat back to the system to further maximize the quantity of hydrogen you would produce with such a coupled system. And so with a roughly 500 megawatt thermal power SMR, you could approximately achieve 100 tons a day of hydrogen production, which was really the main focus of this study, to optimize the use of heat and electricity to maximize the production of hydrogen. So we developed basically an approach in which there is the SMR and its energy conversion system. There is a middle brick which is in between, which covers the transfer of heat and energy between the two systems, and also which takes care of the transients, because you don't want to directly couple all the transients of your nuclear reactor with the transients of your electrolysis system. So this middle system is there to optimize the heat flux in both directions, and also to cover the variations in both of the processes. So we did the first economic approach, this is what Bertrand told you about, and we designed an optimized version of the coupling model, which we patented. Another point which is really important is that if you want to maximize energy efficiency, you have to focus on the use case you want to cover. You cannot design an overall system which covers efficiently all the use cases. So basically, we studied some examples of hybridization use cases, which could be, for example, maximizing hydrogen production, or maximizing the return on your investment. That is, you would sell electricity when the electricity price is high, you would sell hydrogen when your electricity price is low, or you would do some service to a community. You have a specified amount of electricity, of hydrogen to supply to a given network. And so from these three different use cases, you can derive three different technical configurations. And that's the point. You have to study specifically the use case to derive and adapt the technical configuration, which pushes the need for this middle brick, because you're not going to design an SMR for each use case. You're going to design this part of the system, tailor-made for each use case. Then we went further, and like Bertrand told you, we think that in the future, on top of being able to produce hydrogen from low-carbon electricity, we will also have to still provide carbon products, because for some hard-to-abate sectors, you won't it won't be possible to get to electrification or using hydrogen. You will stick to liquid fuels, for example, for long-range aviation. And so we derived specific coupling configurations using carbon capture with different mechanisms, either from biomass, from concentrated sources, or from a direct air capture to provide the carbon from CO2. We still have the electrolysis, and there I must stress that electrolysis needs clean water, which you will also have to produce in the future in regions where there is a water stress. And then you can combine these two atoms and produce the molecules. And one of the big drivers for that is synthetic aviation fuels. Because, as you may know, the regulation, the Fit for 55 package, specify that by 2035, 5% of all aviation fuel has to be synthetic aviation fuel, and by 2050, 35% has to be synthetic aviation fuel. So when you compute these percentages, with the amount of fuel which is used for the Paris airports, for example, which is roughly 7 million tons of kerosene a year, and which is expected to increase further in the coming years, you can deduce that there are very significant amounts of synthetic fuels which have to be produced, so 250,000 tons by 2035, which then in turn requires massive amounts of low carbon energy to be dedicated to this kind of production, massive amount of hydrogen, massive amount also of CO2, which you will have to capture and reuse, and that can be translated in numbers of large-scale power plants or windmills with 8 megawatts at 45% capacity factor. So the main point is that if you have to abide by the Fit for 55 package, by 2035, roughly 1 EPR type power is needed to supply the Paris airport. That's 10 times more for Europe. By 2050, that's 7 EPRs for France and 10 times more again for Europe. So massive amounts of low carbon electricity will be needed if you are to stick with these kind of numbers. And we are developing solutions to achieve that and to upscale also the coupling between the different parts of the systems. Thank you very much for your attention. And we are ready for questions if you want to meet us in the booth.